Hi, everybody. Let's continue with electronics packaging system um, thermal analysis. This one I post for the new video, maybe better uh, sound that is discovered in your computer. Well, for this one, I have lecture I already upload on, with, and this one is series two, and I taught student yesterday and haven't posted on my YouTube yet. Well, let's do problems to get more the understanding. Problem 8.2. A sample of 500 components is tested under continuous operation for a year. The three components that fail at 32, 60, and 390 days are replaced during the test by lambda t or failure rate and NTDF or mean time between failure required NTDF uh, comment on the result. Um, as per the failure rate, we have two cases. One is that the fail uh, replace it with the good one, which you can apply dissipation. And the other one is the problem, 8.3. That's uh, the fail one uh, are not replaces with the good one. So let's get started with the one with replaced first. We can apply lambda t equal to n divided by t1 plus t2 plus t3 and then plus n minus n0 minus n t. And na, that there are three fails. And the first one failed uh, at the 32, the day 32, the day 30, the day 60, and the day 290. So that's going to be 32 plus 60 plus 390, and we have our 500 components. But so you may not be the fail one, that's 3. And multiply by the time, because we test that for a year. So that's what, 1 year have 4 months, and 1 month, that's 30 days. And you also need to convert to hours. So that's why multiply by 24 hours, because 1 day is that's 24 hours. And you get lambda t of failure rate equal to 6.97 10 to the negative 7 per hour. And your NTDF actually is the reciprocal of the failure rate. That's the lambda t. Let's give you 1.43 into the 6 hours. The average time between system breakdown, measuring performance, safety, and equipment design. That's the concept of mean time between failure. Now for the problem 8.3, between lambda t with the components that failed in exercise 8.2 were not replaced during the test. We need to apply this equation. Failure rate lambda t equal to nt divided by n0 t, and the f is 3. N0 component start 500 t, that's the 290 days, and multiply by 24 to get hours. Let's give you 8.62 10 to negative 7 per hour. That's the failure rate. Problem 8.5 determine the probability of success, or PST, as time dependent for the component tested in exercise 8.2. So you have a probability of success equal to exponential negative integration of lambda t dt. That's the equation 8.14. For fails not replaced with the xt, you simply plug in lambda t. And for fails replaced, plug in lambda t. That's the 8.62 10 to negative 7. Okay, so that's about the probability of success or survival probability. That means the chance that your competence is still working. Problem 8.6. Prepare a data representation showing PST for a component with a lambda 0 equal to 10 to the negative third, 10 to the negative fifth, 10 to the negative 7, 10 to the negative 9, 10 to the negative 12. And T on the time, that's the 1, 2, 5, 10, 20, and 50 years. So you want to plot the relation between what PST with the time. So you set up equation according to equation 8.15, with PST equal to negative equal to exponential of negative lambda 0 t. Now let's pick up lambda 0 for 10 to the negative third first. And your times went from 1 to 50 years. So your PST equal to exponential negative 10 to a negative third t. Let's return right. And you get the exponential decreasing for PST, or survival probability, with respect to time. And you can do the rest. So you have 5 plots for different lambda 0 for 5 different lambda zeros. Problem 8.10 derive the system reliability for the series parallel arrangement with a single cross strap. Thus, is shown in figure E 8.10. Note that all of devices shown exhibit the same probability of the failure, PF equal to 0.001. Take a look at the system. You have a total of 24 components, both in series arrangement and parallel arrangement. I separate the system to be system 1 and system 2. Now for components 1, 2, 3, 4, they are in series. So your PS 1 to 4, that's going to be PS1, PS2, PS3, PS4. But since they're PF given, your PS going to be 1 minus PF, because you know PF plus PS equal to 1, right? That's the probability, failure probability, and survival probability. And since they are 4 components in series, so you have 1 minus PF to the power of 4. And the PF is given as 0.001. That's the same as the survival probability of components 7, 8, 9, 10 in series, same as 13 to 16, same as 19 to 22. Now for part system 2, you have components. You have 2 components in series. So UPF 1 by 6, that's going to be same. 1 minus PS by 6. Um, I actually, sorry, for PF by 6, I think I did this one wrong. PF by 6 equal to 1 minus PS by 6. And PS, actually, I should put this one as the PS by 6 because they are in series, right? So if I take a look at this one, PF by 6, oh, okay, I can do that. That's the become 1 minus PS. And PS equal to 1 minus PF, right? That's PF given 0.001. That's there are two components in series. So you have the power to the second. And let's give you PF by 6. That's equal to PF 11, 12, PF 17, 15, PF 23, 24. Be ready to do calculation in parallel. Now for system 1, your PF, that's going to be equal to PF 1 to 4, and then competence. So that's why you have this term. And multiplied by PF 7 to 10, that's competence. Also 13 to 16 and 19 to 22. And since you already have your PS 1 to 4, you can look for PF of 1 4. That's become 1 minus this term, right? Let's give you a PF 1 to 4. And they are PF, they are all the same. You know, for competence 7 to 10, 13 to 16, 19 to 22. So your PF 1, 4. That's going to be what? 1 minus 0.001 to the fourth. And since there are three rows in parallel, so you also have all to the power of 4. And then you can look for PS1. Simply move PS to the right of the equation and move this one to the left. So you have 1 minus this term. That's why I have PS1. That's right here. For system 2, you do the same. 3 rows in parallel. And your PF by 6, you already have just right here. 1 minus 1 minus 0.001 to the second. Okay, and since there are 3 rows in parallel, so you have the whole term to the fourth. And also UPS is going to be equal to 1 minus this term. So that's why I have here. And now for system 1 and 2, they are in series. So you simply work out for survival probability of the system simply equal to PS1 by PS2. And you have this term multiplied by this term. And get the survival probability of the system close to 1. Now let's move to our next topic, 8.3.1. That's the one-dimension heat transfer. From according to equation 8.23a, you have Q equal to negative Ka dt by dx, where Q is the heat transfer rate with the unit of watt. K is the thermal conduction coefficient. Sorry, I'm missing H. That's in the unit of watt per meter degree Celsius. And A is cross-section area perpendicular to the heat flow. And dt by dx, simply temperature gradient of the heat flow. That's going to be the temperature going to be different at different location, at different point on the materials. That's the unit of degree per meter. That dt by dx. And you can work out this one. To simplify equation, you can also write dt become delta t, or t2 minus t1. It simply is the length of the material that's in the direction of its flow. And you have on the right, you have negative q over ka. And you rearrange the equation. You have delta t, or t2 minus t1. That's going to be equal to negative ql over ka. And for delta t equal to qrt. So your RT will simply become L over Ka according to equation 8.24. Okay. And we're going to apply this equation to our chapter 8 for heat transfer calculation in terms of thermal resistant network. Now let's take a look at the equivalent of electrical circuit and thermal circuit. For electrical circuit, you have Ohm's law, delta V equal to IR. And for thermal circuit, you have delta T equal to 2RT. So our V, or the voltage, equivalent to T, or temperature. I, or current, equivalent to Q, or the heat, with the unit of watt. And for R, electrical resistance, that's equivalent to RT, or thermal resistance. You can also work out, for series and parallel arrangement of series connection or parallel connection. For electrical circuit, you have R1 and R2 in series. You have a voltage difference, V1 and V2. And that makes current flow. And current will flow through R1 and R2 at the same amount. Same as the heat, Q. You have a different temperature flowing from higher temperature to lower one, or T1 is greater than T2. And the heat will flow through RT1 and RT2 in the same amount. For the parallel, you do the same, you have I1, the current flowing through R1, and the current I2 flowing to R2. Same as the thermal circuit. You have T1 and T2. It depends on, which one is higher. You know that the higher IT, the lower Q price. Take a look at example. For copper, you have the heat flowing along the length. Here is 100 millimeter, and you have cross section, the width, and the thickness. The thickness is 2 millimeter, and the width is 10 millimeter. You can apply delta T equal to QRT. You need to work out for RT. And RT equal to L over KA, right? For copper, you can look at the table in the book. ACU, or the thermal conductivity of copper, that's equal to 381 watts per meter degree Celsius. We have the heat flowing for 1 watt. Or you want to transfer 1 watt heat. And you can work this one out. Q equal to 1 and L 100 millimeters, that's 0.1 meter, divided by K, that's 381, and cross-section area, that's 2 by 10, and you convert to your meter, so you multiply by 10 to the negative 6. Let's give you delta T equal to 13.1 degrees Celsius. Now for aluminum, the thermal conductivity of aluminum, or KAL, that's equal to 29.4. That's lower than K of copper. You apply this equation, you pick up 13.1, and you put 381. You cancel this one out, and you divide it by K of aluminum. That's 29.4. Give you 169.7 degrees Celsius. So the different temperature is higher for aluminum than copper. And we say that copper is the better thermal conduction. And we need a lower RT as low as possible, because you want to transfer heat, or you don't want inner of your system is too hot. You want the heat transfer out of the system. Okay, so that's what we get from working out of the problem. Now, topic 8.33, heat flow in cylindrical packages. Well, in this case, there you have a cylindrical with the inner radius R1 and the outer radius R2. With the inner temperature T1 and the outer temperature T2, or you can say that's the room temperature, with the length L. In this case, the heat flowing along the radius of the cylinder. Where you apply the same equation, Q equal to Ka dt by dr, because the heat transfer along the radius, and A equal to 3 pi RL, right? If you cut, and this one, that's going to be like what, rectangular. So that's become 3 pi R. Okay, that's the circumference and the length. That's give you the cross section area. You work this out, and you do integration. You integrate temperature from T1 to T2, and the radius from R1 to R2. And finally, you get delta T, or T2 minus T1, become negative 2 over 2 pi Lk, Ln of R3 over R1. You have negative sign because the temperature is T1 is higher than T2, because this is the inner of the system, right? Or you can look for RT, the thermal resistance. You apply delta T equal to QRT, so it's a Q. The rest of the terms going to be Ln R3 over R1, and divided by 2 pi Lk. So that's the RT according to your equation 8.34. Now our topic 8.34, heat flow through layer composites. In these cases mean you have different materials connected in series. Um, you have four different materials, and the most left temperature, that's the Ti, and the most right temperature is T0, or you can say room temperature. And you have the heat flowing from the left to the right, and of course, Qin equal to V0, let it be Q. And you can take a look at this as the thermal resistance network, R1, R2, R3, R4 in series. And you have junction temperature Ti, T1, 2, T2, 3, T3, 4. For you can set our equation Ti minus T1, 2 here. It's going to be a Q of T1, right? Where T1 is equal to L1, the length, divided by K1, multiplied by cross-section area. The cross-section area, they are the same. Same as the T12 minus T23. That's equal to RT2. You add four equations, together. T12 cancel out, T23 cancel out, T34 cancel out. So you have only Ti minus T0 left. And that's going to be equal this four term add up. Or you simply write uh, in the short term, that's going to be 2 or multiplied by summation I equal to 1 to the 4 and Li over Kia, which is the RT, right? Li over Kia, according to equation 8.5. Now, another type of heat transfer is the convection. For RT, for conduction, you know that RT equal to L over Ka, right? Where K is the thermal conduction coefficient. But in this case, your RT is going to be 1 over HA. A is the cross section, and H is the convection coefficient in the unit of watt per meter square degree Celsius instead of watt per meter degree Celsius. So you can apply delta T equal to QRT, right? You move HA to the left. That's going to be 1 over HA. That's your RT for convection. Now, take a look at the figure. You have Ti and T0. This one is T1 and T2. This is the heat transfer by conduction. This one is heat transfer by convection. Also, this one. So for the first one, Ti minus T1, that's the convection. So we need to apply Q over HIA. T1 minus T2, that's the conduction, right? So we have TL over TA. The RT is the L over TA. And for T2 minus T0, that's the heat transfer by convection. So we have a Q over HT0A. Then you add them up. Three equations. T1 cancel out, T2 cancel out. You have only Ti minus T0 left. And on the right, you have Q over A multiplied by 1 over HI. That's the convection coefficient. Plus L over K plus 1 over H0. And if you put U equal to 1 over this term, you can write Q equal to UA delta T. You can work out this and by yourself. So this comes. Where in this case we are T equal to 1 over A multiplied by 1 over HI plus L is K plus 1 over H is 0. That's the equation A equals 0. Okay, so as you left our topic 8.6.3 for next series on my YouTube. Okay, bye.